Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today in lecture 16 we reach the primary idea of the course, the idea of the derivative. Its definition flows from what we did in the previous lecture, so let's review that. We were concerned with the function y equals f of x, and we singled out a point a, f of a, on the graph of that function, and looked at the tangent line to the graph at that point. And the question was, what is its slope m? And we had a formula. The slope of the tangent line to the graph of y equals f of x at the point a, f of a is m, which equals the limit as h approaches 0 of f of a plus h minus f of a divided by h. Alternatively, we could write that as the limit as z approaches a of f of z minus f of a divided by z minus a. Either one of these two limits, when you work them out, give you the slope m of this tangent line at the point x equals a. A quick review of this in this next example. Let's take the function y equals f of x, which is the square root of x, and single out a point at x equals 4. The corresponding point on the graph is 4, f of 4, which is 4, 2. We look at the tangent line to the graph at that point, and the question is, what is its slope? So we could use either one of these two formulas for slope. Let's use the second one. M is the limit as z approaches a of f of z minus f of a divided by z minus a. Let's work this out and see what we get for the slope. The first thing we need to do is note that in this particular problem, in this example, our a is 4. So we'll replace the a that's here, here, and here with 4. We get the limit as z approaches 4 of f of z minus f of 4 over z minus 4. F is the specific function square root of x, so the f of z is the square root of z, and the f of 4 is the square root of 4. So the limit becomes this, and the square root of 4 that occurs here is equal to 2, so let's replace that with 2. We get the limit as z approaches 4 of square root of z minus 2 over z minus 4. In this limit, if you plugged in z equals 4 to the function, you'd get the square root of 4 minus 2 divided by 4 minus 4. That's 0 over 0. So we know in this case that we need to cancel this problematic denominator of z minus 4 that's turning into 0. And you've done enough limits to know that we have a trick for this. Take the conjugate of the square root of z minus 2 and divide it by itself. And you're just multiplying by 1 here. Square root of z plus 2 over square root of z plus 2. So you're not changing anything. But then when you multiply out the numerators, you get the square root of z times the square root of z, which is z, plus 2 square root of z minus 2 square root of z, so those terms cancel out, and continue the foiling. Minus 2 times positive 2 is minus 4. So the numerator becomes z minus 4, and the denominator, it's just these two terms multiplied together. But now we have a z minus 4 on the top and the bottom, so those cancel, and the limit simply becomes the limit as z approaches 4 of 1 over the square root of z plus 2. In this limit, we no longer have that z minus 4 in the denominator that was turning into 0. In fact, the denominator is now turning into the square root of 4 plus 2, which is just 2. So working out this limit, just by plugging in the z equals 4, we get 1 over the square root of 4 plus 2, and that's 1/4. So the answer to our question, the slope of this particular tangent line is 1/4, which makes sense. It looks like rise over run is about 1/4. Let's do this same problem a slightly different way. Instead of taking 4 for our x value, or our a value, let's just keep it at a. So a could be any number on this x-axis. Just call it a, and look at this point, a f of a, or a square root of a. Let's see if we can find the slope of the tangent to the graph of this function at that point. We'll do exactly what we did before. The only thing is we don't have a specific value for a now, but we'll just keep it as a. The slope of this tangent line, m, is given by our formula. The limit as z approaches a, f of z minus f of a divided by z minus a. And f is the square root function, so this becomes the limit as z approaches a of the square root of z minus the square root of a over z minus a. If we plugged in z equals a, we'd be dividing by 0 on the denominator, so we somehow have to cancel this z minus a. Well, we just take the conjugate divided by itself and multiply. And everything's going to work out just as it did on the previous slide, except we have to keep that a in there. Foiling out the top, you get the square root of z times itself, that's z, minus square root of z square root of a, plus square root of z square root of a, and then the last terms are minus square root of a times a minus square root of a, and that's just minus a. So now we're looking at this limit, and we have a z minus a on top and bottom, and they're going to cancel. So our limit becomes the limit as z approaches a of 1 over the square root of z plus the square root of a. And here z is approaching a, and look at the denominator. It's no longer turning into 0 because we canceled that bad term. Applying a limit law and plugging in the z, we get 1 over the square root of a plus the square root of a, and that's 1 over 2 square root of a. So that's our slope. The slope of this tangent line is 1 over 2 square root of a. Now notice that has an a in it. The value of m here depends entirely on what a is, which makes sense because if we change a to a different number, we're going to change the tangent line and we're going to change the slope too. For example, think about a equals 1. So you're way over here. And we have this tangent line. Well, we know our slope is 1 over 2 square root of a. That's our formula for slope. So the slope of the tangent line at x equals 1, or a equals 1, is m, which is 1 over 2 square root of 1, and that's just 1/2. So the slope at a equals 1 is 1/2. Let's take a different value for a. How about a equals 9? And I'm picking perfect squares here. What is the slope of this tangent line? According to our formula, it's 1 over 2 square root of 9, because the a is 9 now. And the square root of 9 is 3, and we get 1/6. So this slope of this tangent line is 1/6, which makes sense. You'd certainly believe that rise over run is 1 over 6. Let's take a different value for a. How about a equals 16? What's the slope of the tangent line at a equals 16? This tangent line? Well, according to our formula, it's m equals 1 over 2 square root of 16. Square root of 16 is 4, so this is 1/8. So the slope of this tangent line is 1/8. So by working out this limit for slope, with a generic a, we get a formula for slope that has an a in it. So in a sense, we're working out all the different limits for all the different values of a in one fell swoop right here. We get all of the slopes. You just plug in the a. So our conclusion is the slope of the tangent line to y equals the square root of x at the point a square root of a is m, which is 1 over 2 square root of a. We've got a general formula for slope for this f of x. It's important to realize that this formula for slope, it depends on a, as we saw up here. It's a function of a. This is a function of a. M equals 1 over 2 square root of a depends entirely on what a is. Different a's give you different slopes. That's a function of a. So what we're going to do is call it a function, give it a name. We already have f reserved for the square root of x that we had graphed up here. So we're going to call this function f prime of a. F prime of a is given by the rule 1 over 2 square root of a. So that gives us the slope. Let's summarize what we just did from a more general point of view. Rather than the function y equals the square root of x, think of a generic function y equals f of x. We said that if we take a point a, f of a on the graph of this function and look at the tangent line, it has slope m, which is the limit as z approaches a of f of z minus f of a over z minus a, also equal to the limit as h approaches 0 of f of a plus h minus f of a divided by h. These limits that give you the slope at x equals a depend on what a is. If you change a, you change this point, you change the tangent line, it has a different slope. These two limits depend on what a is, so we've agreed to call their value f prime of a. It's a function of a. Its value depends on a. So f prime of a equals either one of these limits. So slope now is given by a function f prime of a. Normally when we have a function, you want to put an independent variable of x in there, not a. So let's do that. In this picture, everywhere we see an a, let's change it to an x. I'll redraw the whole picture. We have the graph of y equals f of x, and a particular x value, and over it the point x f of x, and we have a tangent line, m, and its slope would be given by this limit. And notice what we've done is we've changed every occurrence of a to an x. So instead of the limit as z approaches a of f of z minus f of a over z minus a, all those a's change to x's. It's the limit as z approaches x, f of z minus f of x divided by z minus x. So you think about x as being a fixed value, although it could be different values. Think of it as fixed. And then work out this limit, and you get the slope m of this tangent line. Alternatively, we could express it this way, but we're changing the a's to x's. So limit as h approaches 0, f of x plus h minus f of x divided by h. That's the slope of the tangent line. And that slope depends on what x is. You change x, you change this point, you change the tangent line, the slope is different. So depending on the value of x, these limits will equal different values. So that's a function of x that we're calling f prime. This f prime that gives us the slope of the tangent line at x f of x, this is what we're going to call the derivative of the function f of x. Let me summarize this in a major definition. Given a function y equals f of x, the derivative of that function f of x is another function that we're going to call f prime of x. And it's defined this way. F prime of x equals the value of this limit. F prime of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. Alternatively, we could write it this way. F prime of x is the limit as z approaches x, f of z minus f of x over z minus x. And since we are using the slope of the formula for slope in our definition of the derivative, this limit also equals the slope of the tangent to y equals f of x at the point x f of x, just as we had up here. So the picture is this. Here's your point x f of x. Here's your tangent line. Its slope m is f prime of x. where f prime of x is as defined here. This is our big definition for this course, the definition of a derivative. I'll state it again. The derivative of a function f of x is another function called f prime of x, given by this rule. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Alternatively, you could use this other limit. Each one gives you the slope of the tangent line to y equals f of x at the point x f of x, just as indicated in this picture. If you change x here, you're changing this point, you're changing the tangent line, you get a different slope. To get the slope at any x, you just plug in x into the derivative, into f prime, and there's your slope. Let's look at an example using our work from earlier in the lecture today involving the function f of x equals the square root of x. Earlier, we took a point A, x equals a. We looked at the corresponding point on the graph, took the tangent line, and we figured out the slope of that tangent line is 1 over 2 square root of a, which of course, as we noted, depends on what a is. So because this is a function of a, and it's giving the slope at the point a f of a, this is the derivative. F prime of a is 1 over 2 square root of a. That's the rule for the derivative of the function f. Now, of course, we tend to like to have an independent variable of x rather than a, so let's just make that change. Our derivative here is f prime of x equals 1 over 2 square root of x. That function is the derivative of the function f of x equals the square root of x. And it's given us the slope to the tangent at any particular x. This slope right here is f prime of x. So you change x, you change that slope. F prime of x always gives you the slope. Now f prime of x is a function of x, so we could graph it, and I'll show you what the graph looks like. In blue, here's the graph of f prime of x. Think about that for a moment. If you look at the form for f prime of x, if x is a really small number, 1 over 2 square root of x is the reciprocal of a small number, so it's really big. And you can see that happening here for really small values of x. F prime is big. On the other hand, if x is really big, this reciprocal is small, so f prime of x is close to the y-axis for big values of x. And the shape of this graph of f prime of x makes total sense when you think about its meaning as giving you the slope of this tangent line. For instance, let's take this x here and move it in closer to 0, and we're going to look at these slopes, the corresponding slopes, and you'll see that the slopes get bigger and bigger and bigger as x gets closer and closer to 0. Moving an x closer to 0 makes that corresponding slope get bigger and bigger. As x gets closer and closer to 0, the slopes to the graph of square root of x get steeper and steeper, bigger and bigger, and you see the derivative getting bigger and bigger as well. The derivative is measuring the slope. Whereas if you took a value of x that's out here, f prime of x is the slope of this tangent line, and that slope doesn't look like it's very much. It's definitely positive, but what is it, like rise over run would be 1/8 or something, 1/10? And you'll notice that the derivative is about 1/8 or 1/10, this point on the graph of f prime. So the derivative is always giving you slope. Let's do another example. Let's find the derivative of the function f of x equals x squared plus 2. Its graph is a parabola, as shown here. It's the graph of x squared moved up 2 units. To find f prime of x, we use the definition of the derivative. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. In working out this limit, h is approaching 0, so we're getting a 0 on the denominator. So we're hoping to factor an h out of the numerator and cancel with the h on the bottom. Let's see if we can get that to work. Let's examine that numerator. The first thing that you see is an f of x plus h. Now remember, f is the function where whenever you plug something into it, you square it and add 2. In other words, f of a quantity is that quantity squared plus 2. So right here with the f of x plus h, we're doing f of x plus h. It's x plus h squared plus 2. So we're going to replace the f of x plus h with what it is as an algebraic expression. It's x plus h squared plus 2. Then we have a minus f of x. Well, f of x is x squared plus 2. So we have minus x squared plus 2. Let's FOIL things out and collect like terms and see what we've got. The first thing you'll see here is an x plus h squared. We can FOIL that out. It's x squared plus 2x h plus h squared. And then we're adding the 2 right here, so that's plus 2. And then we have minus x squared plus 2. That negative distributes in as a negative x squared minus 2. And what do we have here? Notice there's an x squared and a minus x squared, and those cancel out. There's a positive 2 and a negative 2, and those cancel. So what we're left with is the limit as h approaches 0 of just 2xh plus h squared divided by h. That's all that's left of the numerator. And remember, we wanted to cancel the h on the bottom, but look, we can factor an h out of the top. Both of these terms in the top have an h in them. So we get the limit as h approaches 0 of h times 2x plus h divided by h, and the h's cancel, giving us the limit as h approaches 0 of 2 times x plus h. Now in this limit, it's the h that's approaching 0, not x, but h. So this term right here is just turning into 0. We can apply a limit law here. We just get 2 times x plus 0, or simply 2 times x. So there we have it. F prime of x is the simple function 2 times x. And that's our answer. Our derivative is f prime of x, which is 2 times x. That's our answer, but I want to take this a little bit further to underscore that this 2 times x is really giving us slopes to the graph of f of x, as a derivative should. Let's graph our function f prime of x equals 2 times x. We'll do it in blue. The graph of y equals 2 times x is a straight line, slope 2, y-intercept 0. It's this blue line here. Now remember that 2 times x, that f prime of x, it's equal to the slope of the tangent to y equals f of x at the point x f of x. Now I'll show you what's happening here. Let's take a particular x value, like say minus 2, x equals minus 2. Go up to the graph of f and look at that tangent line at the point x equals minus 2. Definitely has a negative slope, doesn't it? The slope of this tangent line would be got by plugging negative 2 into the derivative f prime of x. So f prime of negative 2 would be 2 times negative 2, it's negative 4. So when you plug negative 2 into the derivative, you get negative 4, and that means this tangent line has slope m equals negative 4, which totally makes sense. You would totally believe that that's a negative slope. It looks like for a run of 1, the rise is negative 4. That derivative is giving you that slope. Let's take another value of x equals -1, and look at the tangent line above -1, the tangent line to the graph of f. The derivative is going to give us the slope of this tangent line. If you plug -1 into f prime, you get f prime of -1 is 2 times -1. It's -2. So the slope of this tangent line is going to be -2. At x equals 0, if we look at the tangent line to the graph of f at x equals 0, clearly its slope is 0 from this picture, and notice that if you plugged in 0 to the derivative, f prime of 0 is 2 times 0 or 0, that's the slope of this tangent. And finally, let's take 2, x equals 2, go up to the graph, look at that tangent line. The derivative is going to give us the slope of this tangent line. Let's see, and it looks like this tangent line has positive slope. Let's see what the derivative tells us. If you plug in 2 into f prime of x, that's 2 times 2. F prime of 2 is 4. So therefore, this tangent line has slope m equals 4. So you can see from this picture that the derivative f prime of x equals 2 times x is really giving us slopes to the tangent lines to the graph of f of x equals x squared plus 2. Let's do another example. Let's find the derivative of f of x equals 1 over x. You're familiar with the function 1 over x. Its graph looks like this. And we want to find f prime of x. And again, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now our function f is the reciprocal function. Whatever you plug into f, you take its reciprocal. So this f of x plus h, it's 1 over x plus h. And the f of x, it's 1 over x. So we get the limit as h goes to 0 of 1 over x plus h minus 1 over x divided by h. And again, in this limit, the h is turning into 0, so we're hoping to cancel it. Now, how would we do this? You've worked enough limits at this point to know how to proceed. You can multiply this entire limit by 1 in the form of x times x plus h divided by itself. Now, we're choosing x times x plus h because that's the common denominator of these two fractions on the top. When you multiply it in, when you distribute it into the numerator, or when you multiply the denominators, you get h times x plus h. And now let's look at what happens when we distribute into the numerator. The x times x plus h times the 1 over x plus h simply becomes an x. And we have a minus. And the x times x plus h multiplied times the 1 over x, the x's cancel, and just gives you x plus h, or minus x plus h. Simplifying this numerator, let's see, distributing the negative into the parentheses, the x's cancel, and we get the limit as h approaches 0 of minus h over hx times x plus h. Our h's cancel, and we have the limit as h approaches 0 of negative 1 over x times x plus h. Now here the h goes to 0, so this h right here is turning into a 0. We get negative 1 over x times x plus 0, or simply negative 1 over x squared. So that's our derivative. F prime of x is the function negative 1 over x squared. F prime of x is minus 1 over x squared. And I've got that graphed over here. The graph of negative 1 over x squared looks like this, as shown in blue. It's the graph of 1 over x squared, with which you're familiar with, reflected across the x-axis because you're multiplying by minus 1. That's what the graph of the derivative looks like. And remember that this derivative is giving us the slope of the tangent line to y equals f of x, this reciprocal function, at the point x f of x. So for instance, if you take, say, this value of x and go up to the graph of f and look at the tangent line, that tangent line has a pretty steep slope, and it's a negative slope. For a positive run, the rise is negative. The slope looks like it's a pretty big negative number, and look, f prime of x is a pretty big negative number. But as x gets bigger, that slope remains negative, but it becomes smaller. That tangent line is getting closer and closer to being horizontal. So although it's negative, it's getting closer and closer to 0, slope 0. And you can see the derivative is negative, but getting closer and closer to 0. So this blue derivative is measuring the slopes of these tangent lines. If x is a negative number, like over here, here's the tangent to the graph of f of x at that point. You have a negative slope, but it looks pretty close to being horizontal. It's a negative slope, but it's fairly close to 0, and the derivative is close to 0. But look what happens as x gets closer and closer to 0 from this side. That tangent slope gets steeper and steeper and steeper, becoming a bigger and bigger and bigger negative number, and that's exactly what the derivative is doing. It's becoming bigger and bigger in the negative direction. So you can see here that this derivative, f prime of x equals negative 1 over x squared, it really is measuring slope of tangent lines to the graph of f of x equals 1 over x. So we've worked out a couple of examples of finding f prime with limits, and you should work some other examples to solidify your knowledge and understanding of this. Practice is always good, and in fact it's essential. In summary, today we have come up with the major definition in this course, the major idea. The derivative of a function f of x is another function f prime of x defined as f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. Alternatively, it equals the limit as z approaches x of f of z minus f of x divided by z minus x. And it equals the slope of the tangent to y equals f of x at the point x f of x, as indicated here. I'll close with some notation that you should be aware of. It turns out that the derivative is so important that there are many, many different notations that stand for the same thing, that stand for the derivative. One of them is this: if y is equal to f of x, then sometimes you'll see the derivative f prime of x written simply as y prime, which makes sense. If y is f, then f prime should be y prime. So that y prime just stands for the derivative. Another notation that you'll see that stands for the derivative of y equals f of x is the expression which you read as dy dx. It looks like a fraction, dy over dx, but you read it as dy dx, and that just stands for f prime of x. I'll show you where this comes from. Let's go down to this picture. If you imagine making a little rise over run triangle for your slope, for your tangent, and call the run dx and the rise dy, then dy divided by dx would be your slope m, f prime of x. So dy dx equals f prime of x. That's where the notation is coming from. And we'll have more to say about this notation later in the course, but for now just be aware that it just stands for the derivative. Another notation that's going to play a big role for us is the following. If dy dx is the derivative and y is f of x, then you could think about this as being df of x dx. We read this as ddx of f of x. And that's just another notational package that stands for f prime of x. But it's really useful because you can think about this ddx that's right here as an operator. It's a verb that says, take the derivative of this function f of x. So take the derivative of f of x, you get f prime of x. ddx of f of x equals f prime of x. So for example, if y equals f of x is the function 1 over x, then as we saw on the previous slide, its derivative f prime of x is negative 1 over x squared. But we're saying another symbol for that derivative is y prime. So y prime is negative 1 over x squared. And dy dx stands for the derivative too. So dy dx is negative 1 over x squared. And finally, ddx of 1 over x is negative 1 over x squared. The derivative of 1 over x is negative 1 over x squared. So as you're reading the text, pay attention to these different notations, and you're going to get fluent with them as you work with this material. Sometimes it can seem a little bit overwhelming. You have to double check and cross-reference to make sure what these different symbols mean. But you'll get good at it fast. You'll internalize it, and you'll use this. It'll become second nature. So that's it for today. Next time, we have an important idea, an important topic, rules for finding derivatives without limits. It turns out that in many cases, if your function that you're looking for the derivative of is a nice algebraic function, there are certain rules that you can use to find the derivative of that function without using the limit. You can bypass the limit. And that's really useful because limits can sometimes be hard to work out. An example of what we'll talk about next time is the so-called power rule, which tells us that the derivative of x to the power of n, the derivative of this power function, is just n times x to the power of n minus 1. In other words, we got that derivative without a limit. We just applied a formula to it. So that's next time. It's good stuff. I'll see you then. And goodbye.